you guys, welcome to my video lab report for Lab 1, which is about constant velocity. Over the course of this video, we will discuss Newton's second law, i.e. the momentum principle, and how it pertains to objects moving at constant velocity. We will also investigate this knowledge experimentally by using tracker analysis, as well as theoretically through the creation of a Python computer model based off tracker observations. Finally, we will compare experimental and theoretical data and discuss why our observations do or don't fully match up with what we expect. Before we can start this lab, we need to discuss Newton's second law, which states that acceleration equals net force over mass, and when we apply this to the equation we know for final velocity, or change of velocity, we get that final velocity equals initial velocity plus net force over mass multiplied by change in time, an equation which serves to explain to us by what magnitude velocity changes as acceleration is applied. However, since in this lab we aren't concerned with an accelerating object, we need to adjust this equation for objects moving at constant velocity. Well, in the case of constant velocity, F net must equal 0, as for an object to move at a constant speed, nothing can act upon the object to speed it up or slow it down. We can see this is true, as when we put 0 in for F net into the equation for final velocity, we get that final velocity simply equals initial velocity, or that velocity remains the same. So, since in our experiment we are trying to model an object moving at constant velocity, we must ensure going forward that there is no net force acting upon the object. And now with that in mind, we can begin the lab. So now, here's our video and tracker. We're only analyzing a portion of the video in the middle where the velocity is constant. As we track the ball's position at relative time intervals, tracker gives us two things to take note of. First, it shows us a table of time values, x position values, and y position values. For this lab, we're only concerned with the time values and x position values. Second, it gives us a graph of time versus x position values, and as we can see, our graph appears to be relatively linear with a positive slope. This is exactly the graph we would expect to have for an object moving at constant velocity in the positive x direction, as it just means that position is increasing in the x direction away from the origin by a consistent value with every time interval. So now that we are sure our video displays an object moving at constant velocity, we can use it to create a Python model that should stimulate the observations we see here. To make this model, we will need the initial and secondary x position and time values, as well as the final time interval. Now, here are a few noteworthy portions of the code used to simulate the experimental observations. Note that we have used initial and secondary time and x position values to calculate the velocity of the ball. Also note that we have set the model to stop running at the final time interval observed within our tracker analysis. And, since we are modeling for constant velocity, we have set f net equal to a 0 vector. When we run the code in Python, we get three separate windows describing the simulated ball's motion. One is a position versus time graph, which appears to look quite similar to that of our tracker analysis, being linear with a positive slope. The second displays a 3D model of the ball's movement, and like our video, shows the ball moving in the positive x direction away from our origin. And finally, the third is a list of time values and x position values. Because we have experimental time and x position values from our tracker analysis and predicted values from our model, we can compare the two against each other to determine how well our model describes our observations. In this graph, we can see that while our experimental data started off matching up with our model data, over time, the two lines begin to diverge more and more. And our experimental data is not actually linear, but appears to be curved at various points. So, what does this mean? Why do the two differ? To understand the difference, we have to talk about real motion and individual forces. Our model is incorrect in that while it does describe an object moving at perfectly constant velocity, it does not truly describe our experimental observations or the object's real motion. This is because it doesn't take into account individual forces acting upon the ball that cause for F net to be a value other than 0 at different time intervals. The model describes a perfectly round ball moving over a perfectly smooth surface, but in the real world, our ball is not perfectly round, nor is the surface perfectly smooth, and friction between the ground and the ball, as well as normal forces acting upon the ball in the x direction at ground deformities, cause for F net to not truly be 0. For our model to actually describe the ball's real motion, we would have to take into consideration all of the individual forces acting on the ball at different points when creating our model. Now to answer final questions. The first question asks if you can know how many pushes and pulls are added together to give 0 net force in the case we observed. I determined it's not possible to know how many individual pushes and pulls are added together to give you 0 net force, as it's impossible to know what forces act on the ball at any given moment. And the second question, they asked what would happen if we were to flip the axis. If we flip the axis, we will get the same x position data, except it would be negative. The ball would travel at the same speed, it would just travel in a different direction.